I made a video presenting a solution to the 1995 IMO, problem number 6, but I had to evaluate two expressions that I passed off as well-known. But it's fair that I give you a proper explanation. I made a video for one of those expressions, but this is the other one. I'm still in the trenches. So let's get right into it. So the context was that we have the complex number omega equal to e to the I 2 pi over p, and p is an odd prime number. Now, you want to evaluate this summation. Now, of course, at the beginning, there doesn't seem to be a straightforward path or beginning to the solution. But we see that we have a binomial and a positive integer power. So why not expand it with binomial theorem? That way we can analyze each individual term. So by the binomial theorem, this is equal to the sum as j goes from 0 up to p minus 1 of the sum, let's say k going from 0 up to 2p of 2p choose k, and then times omega to the jk by the binomial theorem once again. Okay, so we have double summations. Not very fun. But here's the thing. We can actually exchange the order of the summations. In fact, we can actually write the sum as k goes from 0. Let me write that again. K goes from 0 up to 2p of the sum as j goes from 0 up to p minus 1 of the same expression. And in case you are wondering why we can write it like this, why this is equivalent to this, well, that's because each of these indices, well, they are independent of each other, and they are finite. So there's no problem at all with swapping the order of the summations. Okay, now why did I do this? Well, notice that this 2p choose k, this binomial coefficient, is independent of the j variable. So we can just take it out. We can take it out of the first summation. So this would be equal to the sum as k goes from 0, let me write that equal sign again, k goes from 0 up to 2p of, we take that binomial coefficient out because it's independent of j, and then times the sum as j goes from 0 to p minus 1 of omega to the jk. All right. Now, do you see what this expression is? It's a geometric series. Now, does this mean that we can use the geometric sum formula? Does this mean that we can just write this thing as omega to the kp minus 1 over omega to the k minus 1? Not so fast. And the reason is this. Notice that this expression is within this summation, and this summation goes from k equals to 0 up to 2p. Notice that when we have k equals to 0, well, in the denominator, we have omega to the 0, and then that's 1, and then 1 minus 1, that's 0. We have a 0 in the denominator issue, which is a problem. So your answer will not be rigorous if you use the geometric sum formula. And that's not only for k equal to 0. Remember, we have omega equal to a pth root of unity, meaning that omega to the p is equal to 1. So when k is equal to p, well, this denominator is also 0. And similarly for k equals to 2p. So this is not going to be acceptable. So what can we do? Well, let's first erase this. Well, what I am about to write might get a bit messy, but it's actually going to help us understand the next step. Okay, so bear with me. What I have done is I have expanded this first summation. This summation from k equals to 0 up to 2p, I have expanded that. So no more k's. This is the expanded form of that first summation. Now, why did I do that? Well, it's because you can actually evaluate the sum as j goes from 0 up to p minus 1 of omega to the jk based off of two cases. Note that this sum is literally the same as this geometric series. So we can evaluate this based off of two cases. The first case I will consider is when p divides k. And because omega to the p is equal to 1, and if p divides k, well then this would mean that omega to the k is 1, right? So this would mean that this sum would just be a sum of a bunch of 1s, namely p1s, because this goes from j equals to 0 up to p minus 1. So this would be equal to p, of course, if p divides k. Now, I'm sure you're wondering, what happens if p does not divide k? Well, yeah, not as easy, right? But consider this. Notice that since p is an odd prime number, then e to the I 2 pi over p, that will be a primitive pth root of unity. Now, primitive roots of unity are very special, and that's because if you take one and raise them in successive powers, then you will eventually get the set of all the original roots of unity, just in some order. So, what does that mean? Well, that would mean that as you take the power j goes from 0 up to p minus 1, as this power ranges from 0 to p minus 1, right? This omega to the jk will eventually sum across all pth roots of unity. And trivially, the sum of all pth roots of unity is 0. So, the sum would be equal to 0 if p does not divide k. Now, can you see why this is so useful? Well, that's because within all of these terms, right, all of these terms that I've written, they will only have a non-zero value if p divides k. If p does not divide k, then the summation is 0, and so the term won't have any value. Now, for what values of k will we have p divides k? Well, k equals to 0 is one of them, so k equals to 0, also k equals to p, and k equals to 2p. Those are the only values divisible by p, because it goes from 0 to 2p. So therefore, among this entire summation, this has no value, this has no value, and finally, well, these three values are the only ones with actual values to consider, because all the other ones are going to be 0. So let's evaluate these three summations. Firstly, this is not hard at all. This 2p choose 0, of course, is 1, and this sum, well, is equal to p. Because remember, we had this summation to be a sum of a bunch of 1s. And over here, for this one with k equals to p, well, this 2p choose p, can't really do anything about that, so just write 2p choose p. And then this one, of course, is again p. And then this last one, this 2p choose 2p, well, that's 1, and the summation is equal to p. And we just have to add them up. If we add them up, this will become 2p choose p times p plus 2p. And this is our final answer. This is our answer to the summation. And there we have it. If you have worked with complex numbers for a good amount of time in math competitions, hopefully the techniques over here aren't too alien to you. But of course, if you have not, then don't worry. Still, if you learned something, that's great. Even if you did not understand everything, if you have learned something from this video, then that is already really good. So, I thank you very much for watching. If you found this interesting, then please consider dropping a like and subscribing. Thank you very much. Bye.